Yeah, good morning, afternoon, good evening, everybody. It's Wednesday, so EMinar day. Excuse me. And today we're going to have a wonderful EMinar from Juliane Huebert on space weather, GICs, and MIT. Just to whet your appetite for upcoming EMinars, next week we have Colin Farquharson continuing on our theme of inversion. Colin will talk at midday UT time. And then the week after, NASA Mekbel explaining, giving us a user's guide on the most used 3D inversion code in academia. And the week after that, Vladimir Pozyarev on neural networks, EM inversion using neural networks, so another deterministic method, probabilistic method. And then Kerry Key telling us about MAR 2D EM, which will be excellent, followed by Randy Mackey. So as you can see, we're lining up a whole bunch of inversion type talks. And then we have a gap. We've got one person to fill in, and then we had somebody drop out. So I'm just going to jump in and give a talk that I presented in China a few years ago on Publish or Perish. And then finishing off the inversion at the moment anyway is Malcolm Sambridge, who will give us a general talk on optimal transport. So just to remind everybody, you can register for all of these EMinars on the EMinar webpage, and you can see prior ones on that webpage, or you can go onto the YouTube page. And finally, you're on a Zoom webinar. You can send a chat to people. You can raise your hand if you want to speak at the end, and you can send a Q&A, and you can do this on the fly. And if Juliane has time to answer your question on the fly, she'll do it on the fly or at the end. So today we've got Juliane Huebert talking on space weather, GICs, and MIT. And just to give you a bit of background on Juliane, she's a researcher specializing in MT at BGS up in Edinburgh. She did her undergrad in Potsdam, sailed to Sweden for a PhD in Uppsala, and then did work at University of Alberta with Martin Unsworth. Then moved to Edinburgh University, studying volcanism, and since 2018 has been focused on the solid Earth's response to extreme space weather. And this is a super important topic. So I'll just stop sharing and invite Juliane to share your screen now and make yourself live. And I'll disappear.
Hello. Good afternoon, everyone, and thanks for joining us on this Wednesday for the EMinar, which I sort of colloquially entitled Space Weather, GIC, and MT, but actually it should have a more verbal, more prosy title, something like Space Weather Impacts on Ground Technology and the Role of the Solid Earth Response, to be a bit more respectable. But basically, I just want to give a bit of an overview of this quite exciting topic we're working on, and highlight some recent findings and some trends that are going on in the community, in the EMI community. And then I would just want to present some of the work that me and my colleagues at the British Geological Survey are doing. So it's going to be like a big mix of everything. And unfortunately, 1 hour or 45 minutes isn't really enough to talk very comprehensively, or not comprehensively, but very exhaustively about all the different topics there. So just see it as an invitation to be curious and to find out more. And there are lots of resources out there, and I'm also happy to get in contact with people if there are more questions. So my talk has kind of 3 different sections. One is, of course, an introduction to space weather, which is like it's not a very new topic, but at least in my mind, it was when I joined DGS 3 years ago. So there's going to be a couple of slides about that and what it means and how we observe it, and what data is involved and what we know from historical records a little bit. And then I'm going to go to the role of the solid Earth, where MT is going to play some role, namely with the estimation and modeling of the geoelectric field. And then I'm going to talk about the actual impacts on ground technology by space weather, which is something of the main topics of our research at the British Geological Survey. And these are just like some more pages where we can find a lot of more information. So a little bit introduction into space weather. What is actually space weather? Well, it's something like a novel natural hazard. So we know what natural hazards like landslides and earthquakes and volcanoes, obviously. But that has been classified as a natural hazard is a relatively new thing. For example, in the UK, it's been on the risk register only since 2015 or slightly before that. And that's, you know, pandemic influenza is where we are right now, but this is where severe space weather sits. So just a couple of slots below that in a diagram that says something, how likely are things to occur and how big would the overall impact actually be. So space weather has been recognized as a hazard, and of course it has something to do with space. And kind of the official definition is that it's solar wind disturbances that affect the Earth's space, atmosphere, and surface environment, and that can disrupt technology. So it definitely has this component that it is a hazard to our technology, and technology is something we can't really think away these days. Just today, Edinburgh Council has decided to rip up the street in front of my house to put in some fiber optics cable. So if something were to get disturbed there, we couldn't be talking. We couldn't have any meaningful interactions right now because we're bent to our homes. Yeah, coming back to space weather, it's of course something that has to do with the things that happen on the sun. And these are just some pretty images of the solar cycle, which is a 22-year cycle of activity that is described through a couple of things that we can observe on the surface of the sun. So what are the causes for space weather or for extreme space weather? It's what happens on the surface of the sun. Namely, one could be sunspots. And this is also how people observed and correlated solar activity with what can be observed on the surface of the sun. Namely that the sunspots change polarity every 11 years and the full cycle takes 22 years. And you have these dark, positive and negative bright regions on the surface of the sun. And they are basically where the magnetic field lines of the sun connect and come out of the surface of the sun. The other cause for space weather or for disturbances in the solar wind are flares and coronal mass ejections, because our star is obviously very active and also emits a lot of not just energy and light, but also particles sometimes. And solar flares can be seen, for example, the Carrington event, something that was in the ad for this seminar today, was caused by a solar flare. And then there are solar coronal mass ejections, something that can also be observed with satellites. And you see an image here of an eruption from February 2000. And just because we are looking right at the sun in this image, you can see the explosion of this material here away from the sun, hopefully not interfering or coming into the path of the Earth. Yes, and coronal mass ejections, they cause charged particles in magnetic fields to escape from the sun and be transported together with the solar wind towards the Earth. And that's just a nice side effect. Everybody has heard of Aurora Borealis or Northern Lights that you sometimes can see over in higher latitudes. I've seen them in Canada and sometimes in Scotland. And then there's also this phenomenon called Steve, which apparently also has to do something with, or is caused by similar physics happening in the magnetosphere than Northern Lights. Yes, so coming back to the solar wind, well, the interaction of the solar wind with the magnetosphere is actually the part that says how impactful the emissions from the sun are, if solar flares or coronal mass ejections or just sunspots that cause faster bits in the solar wind will actually impact or become geo-effective. So that's the physics about the interaction of the solar wind with the magnetosphere, and that's of course a subject of science just in itself, and there's a lot of research being done. And basically, takeaway message here might be that solar wind carries with it the interplanetary magnetic field, and if that, when it reaches our geomagnetic field, has a negative component in the BZ, then it gets into the region where it can couple with our geomagnetic field and cause disturbances. And for example, this is a modeling code that's been used by Imperial College London about magnetohydrodynamic modeling of the magnetospheric convection caused by the interplanetary shock arrival. So something very complicated, but it's something that will tell us how geo-effective actually eruptions from the sun can be. So how does space weather actually impact the geomagnetic field? Well, I gave it away here just saying that it has an impact and it can be observed on the ground. These are 2 magnetograms collected at one of the UK geomagnetic observatories up in Lerwick in Shetland. And on the left-hand side, you see something called a quiet day, where you can see the diurnal variations in the horizontal parts of the magnetic field. And you can see also the vertical component here. And that in comparison to a magnetogram being recorded on a so-called stormy day, not so quiet day when the sun was very active and there was coupling between the solar wind and the magnetosphere. And you can see that the scales are very different, and also the effects that the active geomagnetic field has, the disturbances are on a much bigger scale than the normal diurnal variations. So it's something that is very, very visible in ground observations. And in fact, ground observations are used to classify geomagnetic activity and the effect of space weather. And many of you probably know this, that geomagnetic observatories are spread all over around the world, and most of them deliver very high quality and sometimes even in real-time magnetic field data. And there's a really huge database of the last decades, up to 100 years maybe, that can be used to study geomagnetic activity. And of course, it's being used for very many different things, to look inside the Earth and to look up into space, because it's a superposition of both things, of internal and external field sources. Coming back to magnetic activity and how it is used to classify geomagnetic activity, as something called geomagnetic indices, and those can be calculated from the activity or from the changes in the magnetic field observations. And they are classified in different scales. NOAA is using something called a G scale. That's something that they use in the US. And BGS uses KP values, which is a planetary K index value, which is kind of an estimate of the activity in a 3-hour bin. And there are certain thresholds which say something about how much activity is going on. And you can just see it's quite intuitive that red means it's very, very active, whereas green and blue mean it's like very low activity. And that's something that a lot of places put out as forecasts. So in the in Europe, there are quite a lot of agencies that send out these geomagnetic forecasts. And in the UK, it's the Met Office and the British Geological Survey, who say, okay, we're expecting, based on a long protocol of looking at satellite data and activity on the sun, what people think is going to happen with the geomagnetic field. And how this is interacting with ground technology is kind of what I want to hint at later, or where I want to get to later. But just to say that there are a lot of places on the internet or agencies that deliver these services and these forecasts, and anybody who's interested can study much more about this. So this is kind of a nice slide to say, okay, what's actually causing us concern? Why do we think that space weather is impactful on our technology? And that's kind of a summary of all the places that we think that space weather can have harmful effects. Of course, it's everything that is in space already, like satellites and GPS signal might be infected, and then planes and the orientation of planes, these things, and navigation in planes can be impacted. But what I want to talk about is more like what's happening in the ground, because that's where solid Earth geophysics will play a role. And mostly I want to talk about geomagnetically induced currents in power systems, and also what can happen in pipelines. So a couple of slides from one of my colleagues who's doing a study on that, how can we model those effects. And space weather effects have been reported like over the last couple of years, in especially higher latitude countries, obviously like Canada, Sweden, Finland, the UK, but it's definitely also under surveillance in the US and in New Zealand. And there's research being done in Spain, Portugal, South Africa, Japan, China, obviously, and even found one in Ethiopia, which I didn't know that the Ethiopian power grid could be subject to GICs, but there are studies and model support. So why does space weather cause grid problems? Well, I was trying to say that we have increased activity in the geomagnetic field, and that also induces a lot of electrical currents in the ionosphere. And these time-varying currents, of course, induce more magnetic fields, as we could see in the magnetograms observed in the geomagnetic observatories. And these induce additional electric fields in the ground. And those electric fields can actually be quite big, so they can be much bigger than the normal background telluric currents that we often observe in magnetotelluric studies can be. And these induced electric fields can enter into infrastructure like power lines or like railways, which are these very long conductors made of metal, grounded only every couple of kilometers, every tens of kilometers. And so you have these extra currents flowing in your infrastructure, and going to report a bit later like what the impacts could be. For example, in the power lines, it can be that like there's a saturation in transformers, and transformers are these endpoints of power lines. I'll have a picture later, just for you to imagine how a transformer looks like. And you can cause like overheating and decay, and in the worst case, actually, you can have transformers being blown out, and that can cause net instability and can have a lot of effects on the power grid, because it's a very complex system that depends on all its parts, basically. So it's not just as trivial as observing one current in one line and then one current going into the ground or not. It's actually the whole interplay in the network that needs to be modeled and monitored. The other infrastructure I want to mention is the gas pipelines, and it's not exactly GICs, it's something called a pipe to soil potential that has to do how gas pipelines are protected with some cathodic current, voltage to protect it against corrosion, and that can interfere with those induced electric fields and can have negative influences. There are also reported disturbances in railway communications, but it's a bit difficult because the railway industry doesn't like the reports or the records that they keep of disturbances in many countries, at least in the UK, aren't really like in the best shape, so you can pin them down to geomagnetic activity. But it's definitely reported that there can be some impact from space weather on railway communication, just because it's the same type of infrastructure that you have. This is a dramatic picture that everybody always shows when talking about GICs. This is a blown out transformer, which is like this big piece of wire, and you can see it definitely took some heat there. And the biggest reported impact that we actually have in like in current days, when there were connected high voltage power grids everywhere, is the power outage reported in Quebec in 1989, and there was quite a dramatic cascading effect where different parts of the network suffered from blackout. And it's actually not true that it wasn't a 2-day blackout. It was a couple of hours, I think. And then there's another reported from a transformer in Sweden where there was definitely a blackout, which was due to geomagnetic activity. Yeah, how bad could it get? That's always the question you get from people that want to assess the risk. And it's not only us scientists or politicians that have thought about that. It's also already out in the field, not just of Hollywood, but also from TV script writers. And because everybody knows the core, probably everybody has seen how bad it would be if the Earth wouldn't have a geomagnetic field anymore, if there was a reversal. But recently there were also like 2 shows on British television, which I think were quite watchable because they dealt with a catastrophic event from the sun, and one was portraying science really, really badly, which was one called Hard Sun. Really doesn't display at all how science works, because it was only these 2 police officers that found out that there was something wrong with the sun and nobody else knew. Whereas in that other show called Cobra, which funnily enough had Begbie from Train Spotting as the UK Prime Minister, which kind of says something about political climates. That show actually got it really right up to the point where the COBRA, which is kind of the government committee dealing with catastrophes, is asking the geophysicists, and does the interplanetary magnetic field have a positive or negative southward pointing component? So that was really good for, when it comes to science. Anyway, so it's not just us scientists, it's actually out there already. How large it actually can get, the event that is always cited is the so-called Carrington event. And that was the largest magnetic storm on record, actually where we have records. Because in 1859, there were already a number of geomagnetic observatories around. This is the record from Greenwich Observatory in London, but there were also one, I think the one in Rome and Italy was running, and one in India. So, but the problem, of course, is that this data isn't in digital form, and a lot of the times the actual interesting part was going off scale. So you can see that here, that you can see there's a lot of activity, and the needle is moving very, very fast, and then it just goes off the paper. So even though we have records of that storm, and we have a lot of reports and that affected telegraph lines in the whole of the US, and that auroras are visible as south as Hawaii and Cuba. Actually, the actual data we have is it's not so big, but this is usually used as kind of the extreme event that could happen. And for example, there was a study a couple of years back involving some of my colleagues, assuming if this is if this event were to take place nowadays, how big of an impact would it actually be on UK economy? And they came to a conclusion that an event of this size would probably cause 4% of the transformers to fail or to take some damage, and the gross domestic product loss would be something about 16 billion pounds, which sounded a lot at the time, but yesterday I did a little Google search what the actual deficit is of the UK budget just caused by COVID-19, and that's, you see it's kind of at least 1 or 2 magnitudes bigger. So anyway, that probably reflects the place that space weather hazard investigations have to take in respect to pandemics and other diseases, but it's still there somewhere. So it's quite a big, it used to be quite a big number, I thought. The March 1989 event is one where we do have a bit more data, and there's quite a lot of studies being conducted on this one. And this is just to summarize a little bit. It's from David Butler's paper from 2 years ago. I thought it was quite instructive because he's trying to recreate some of the data that would be available today, but wasn't available back then, which is the solar wind speed. But what we do have is the magnetic indices from that time, and he also collected all the power outs in different countries and different systems, and there's one that correlates, this part of the graph correlates it to magnetic latitude. So I think that's quite interesting that we have a couple of extreme events in the digital age that we can actually study, and then there's historic events where it takes a bit more reconstruction. I know that people are trying to reconstruct what happened during the Carrington event and what the effects would be and what the data would look like. Data that we nowadays can't observe because there are quite a number of satellites and observations directed towards the sun, and being cautious of space weather events. Yes, now we have to somehow come back to ground effects again, and this is basically what I want to come back to. So what data do we actually need to quantify these ground effects? And for GICs, for geomagnetically induced currents and power lines, we need to know something about our infrastructure, obviously. That's obvious, but it's not trivial. So just saying that we need a model and representation of the topology of the power grid. And we need to know the ground electric field. And this is where geophysics and solid earth geophysics and magnetotellurics can come into place again. Because basically what you need is to estimate and to model geomagnetically induced currents in the power grid, you need to know the ground electric field along those power lines so you can integrate them, so you can plug it into the GIC estimation. Yes. geoelectric field, you would say, that's something I know, because most people that do MT know about it quite a bit, because we're measuring it every day. We're putting out our electrodes. So you can see two of my colleagues being hardy at work, putting in an electrode into the ground. So that's something we're doing every day. Unfortunately, the difference between doing it every day with an MT survey where you leave them in for a couple of days or a couple of weeks, it's not quite the same as observing it long term. So there are different ways to derive the ground electric fields, and this is really only a very rough and very shortened version of how to derive the ground electric field. Of course, you could do measurements, and there are certain places in the world where people do long-term measurements of the ground electric field, and those are quite important. So there's a couple of places in the US, and there's 2 observatories in Japan, and I think in China as well, where they've done it for decades. And this data is quite interesting, but it's also, as everybody that has done MT surveys knows, that there's a lot of noise and instrumental drift and decay of probes and stuff. So it's not as straightforward as the magnetic field observations are. So there's much less standards connected with it. Nevertheless, in the UK, we do have 3 places where the ground electric field is being measured, and that data has been hugely helpful in all our efforts to classify space weather events and the effects on infrastructure. So 2 other ways, just like to briefly introduce them, are like you basically, you can calculate your ground electric field if you do have a model of your electrical conductivity. Or a more elegant way, and something we're going to talk about a bit more maybe, is you just use the magnetotelluric impedance transfer function, because that's the transfer function between electric and magnetic fields. There will be some caveats and some restrictions, because to be exact, this is only valid in the plane wave approximation. So, and if the plane wave approximation is violated during geomagnetic storms because your aurora oval comes further down, that has impacts, and I don't really have the time to talk about it much, but there, that's definitely a limitation. But nevertheless, in its beauty of being just a multiplication and frequency domain, it's a very easy way to derive an approximation of the electric field if you do not have any measurements. But you do have a magnetotelluric transfer function, be it from real data or from a model. So just to say, estimating the ground electric field, there are very many different techniques out there. People do a lot of different things. And Huebert wrote this really amazing review paper a couple of years back. I think it was after a talk given at the EM induction workshop in Denmark. So, and she like summarizes, I mean, all of them really. And there's a lot, because a lot of people are interested in this nowadays, now that space weather events are put out to be a geohazard. Just gives us a bit more boost sometimes with finding funding and justifying our work. So basically, I mean, this is one of the many flow charts. I am going to show a couple of them because, there's people I like to show them, because if there's a lot of data involved and a lot of different processing steps, flow charts are the way, but maybe you can get a bit sick of them by the end of the talk. Just to summarize, basically what you do need if you want to estimate the ground electric field, and you cannot measure everywhere, is you need some magnetic field data, because that's the source. Like the magnetic field data during a geomagnetic storm should be directly related to the electric fields that you would measure if you had probes out. And you should have some information about the electrical conductivity, and that may either be a full conductivity model, 3D model, 1D model, 2.5D model, whatever you have, or you have the MT impedance, which is what a lot of people use. So what kind of electrical conductivity model? Well, it really depends on what you have. So if you're as lucky as the people in the US, and you have US array and you have thousands of empty sites in like regular gridding, then it's fantastic. But not many people have that. I mean, Australia is getting there. We heard in the talks of Paul Bedrosian and Stefan Thiel about their efforts. So they're creating really great data sets that can be used for a lot of things. Other places on Earth don't have that great data sets, but some have really good data sets. For example, the one in Finlandia isn't too bad. And the team in Sweden is using it's 3D model based on SMAP, which is compiled of a lot of different empty surveys without it being a 3D inversion model. And then there's, of course, always depending on the scale you want to look at. If you want to look at a global evaluation of electric fields doing geomagnetic storms, you need a global model, and that, of course, comes with a lot of different resolution points. And there's one example here from the group in Zurich. Yes. Well, but instead, if you're using just the empty impedance, that has a couple of advantages, being that it does avoid ambiguity that comes from inverse modeling. So everybody that has done inversion of empty data, and that's of course the focus of the seminar series as well, knows that just because of the nature of the physical problem, there are ambiguities, and there are also like biases by people choosing a way to do inverse modeling. So there's no one true way to do it. There's a lot of ways that should lead to similar results, but there's not just one way. So you would avoid that if you just use the empirical relationship of electric and magnetic fields via the empty impedance. And it's of course also very quick. It's a very quick computation. You don't have to solve for electric fields in a very finely discretized 3D model. You just have to solve Fourier transform and a back Fourier transform. That's basically it. And actually, I would say the accuracy is quite high. There are some more things to look at how you can increase accuracy by using, for example, interstation transfer function. That's something that Joan Campagna has showed on the British Isles and Ireland. And there's also ways to make it almost real time, because what a lot of stakeholders in our research would want is a very close in time estimate of electric fields and of space weather effects. And there's a good paper by people from Oregon. And then Anna Huebert also has a way of doing it in time domain instead of frequency domain. So there's different approaches out there, and all quite promising, and all like with, I would say, quite good accuracy. In the UK, it's a little bit different because we have the problem we do not have a lot of empty data. And what my colleagues have been doing so far is actually using a so-called thin sheet model, which is a little bit like what the Swedish people are using based on old MT data and some airborne electromagnetic data. There's some interpolation from geology. So it's the assumption, and it's a little bit is a synthetic model. It's not completely based on data, but it's a very useful model because the thin sheet model can be put into electric field computation. It's very quick because you just have to solve for your thin sheet, and underlying there's some 1D electrical conductivity, which is based on the geology. The other thing we use in the UK is we use the anomalous magnetic fields, which is recorded at the observatories, and then there's a number of other variometers measuring the changes in the magnetic field out about in the country that give quite good coverage, and then using special techniques, you can interpolate that over the whole modeling domain, which is the British Isles. So, and from that, we can compute the electric field relatively quick in all places in a 10 by 10 kilometer model across the islands. And from that, we can calculate geomagnetically induced currents. This is just an example how during a storm, the distribution of electric fields across the British Isles might look like. We have in the X or in the northward component, you have quite high currents flowing here in Scotland, and then the eastward component is somewhat weaker. For the September 2017 storm, which is one of the last big storms we actually had. Just to say that those other values that we compute to be the maximum values reached during that storm. So something like between 1 and 2 volt per kilometer, which is still quite a bit. All right, and then we did a little study of comparing the thin sheet model with what the impedance could predict in electric fields. And that's just saying that using the impedances gives a much better fit to the observations, because we do have the geoelectric field observations from the observatories. But the correlation with the thin sheet model isn't too bad. It's something we're just dealing with right now. And of course, as an update, we got some new funding to collect more MT data to actually be able to have a truer model of the underlying conductivity as a base for our electric field computations. Just unfortunately, I haven't been able to do any field work in the last year. I guess many people feel with me there, but it's been postponed, and we're just waiting for it to happen. All right, now we took a little slide through the geoelectric field calculations and how many people are doing it, or just the principles of it. And basically what I want to focus on in the third of that talk is about the actual effects on infrastructure. I want to start with GIC modeling in the UK, and it's just like a little tour of what has been done in the past years and how we can model things using the data that we have. So there's of course more potential if you have more data and you have new approaches that these models can be improved. But just to say, this is already quite a good place to be in. And geomagnetically induced currents, I said, okay, we need to know something about our systems, about the power grid topology. And that's something my colleagues have been building up in the last, I think, 10 years or so. So they started with something very simple, and then they made it more realistic by adding more nodes, and like because that data is something that is only half in the public domain. So the national grid, which is the grid provider in the UK, doesn't just hand out, the position of all the transformers and substations and lines and so on. So there's a lot of it is from public domain data, like shape files where power lines are running, that's from the public domain, but that's only like partially available. So we do know a lot of things about the grid, but we don't know everything. So some things are just assumptions, and some things we are like iteratively making better, because as it turns out, actually the devil is in the details. So to accurately model GICs and transformers and in the lines, you actually need to know like really good detail about your grid. And I'm going to come back to it in one example where I really showed that you have to know quite a bit about it to get it quite right. Yes, just to say, so my colleague Gemma Richardson did the study about what would GICs look like in the model that we have using the electric field estimates that we have. What would it have looked like for the March 1989 storm? And you can see there in some of the substations, especially around the coast, you see some really high currents flowing that probably did cause some damage. And in the future would definitely also be something to look at. Which brings me to the point that GIC measurements. So like everybody, we are able to model GICs, but then it's a question, how do we validate this? Can we actually put it to the test with some real data in the UK? Unfortunately, there's only like 4 places that we know of where we can get GIC observations directly from a substation, where somebody went and connected, this is something called a whole probe to a transformer. So transformers are these things, like windy things in the substation. Funnily enough, we have been driving around sometimes to see like if lines were connecting to certain transformers, because the information that is out in the public domain isn't always reliable. So just on top. And I guess there's something that has to do with national security. And I know that colleagues in the US also had problems like assessing this information. And it's just in some places where the network providers are actually more open to collaborations. I mean, at least we have the ear, and they provide us, that's some Scottish Grid, they provide us with these measurements when we ask for it. So, and that's a study from one of my colleagues a couple of years back, where it actually could utilize GIC measurements from 4 places. But that's of course just 4 places in Scotland. So that's not very representative of the whole of the UK grid, which is connected everywhere. So we really felt the need, we need to expand the data set. And that's possible by using the so-called differential magnetometer method, which was first used by colleagues in South Africa. And it's actually using quite a simple mechanism by measuring the magnetic field under a power line and measuring it a couple of 100 meters away. And by assuming that you have this extra direct current flowing in the power line, that you would actually get an extra magnetic component that is related to that current in the magnetometer under the power line. and you wouldn't, I mean, we did some studies, some sensitivity studies, how far away this would need to be, so you wouldn't see the effects anymore for certain line current strengths. And then the engineering team in our group went and built some bespoke magnetometers, differential magnetometer systems that we then employed around the UK. And well, that's also another fieldwork story I don't want to bore you with. But basically, this is how the system looks in the field. It's really just a very, very portable system using a flux gate magnetometer. It's just the hardware that we're using. So these are like things you can buy off the shelf. It's just putting it all together and actually making it real time, which took a little bit of, not a little bit, took a bit of engineering, because this data is actually being transferred to the office in real time, because it's using the 4G, or usually the 3G mobile network connection. So we get this data in real time, which is quite nice, because it's not only measuring the GICs in the grids, it's also extra magnetic data from variometers. Basically what you have these tiny little flux gates, which are quite neat, and they get buried in the ground, so they stay relatively stable with temperature. And yeah, this is just a seismic digitizer, 3-channel digitizer that collects the data and that you can actually access via the modem. Yeah, and couple of slides on like what we kind of used as a proof of concept for the DMM. So we had like one event where we had one side of these installed already, and that was actually the largest event in the last 3 years, which is the August 2018, and I think it was just a G3 on the NOAA scale, so it wasn't even that big, but it was definitely some activity, and we had one instrument out, so that was good because it showed that what we're measuring is actually line GIC. So from just from the difference in the magnetic field measurements, so in the 2 horizontal components, you have to do some rotation, and you have to take into account how your power lines are actually going, like, you know, so like how many lines you have and how high they are, like the geometry, and the thing we assumed in the beginning is also that you would have balanced currents. And for that G3 event, we actually got something like 25 amperes as line current, which isn't exactly what is being measured in the ground probe. So that's also something we want us to say, that what's measured in the ground probe, in the transformer, the thing that is actually damaging, it's not exactly what's being measured under the lines, because yeah, it's again about the topology, how many lines actually do feed into a transformer, and how are GICs, line GICs balanced within the system, because that's not, as I say, not so trivial that everything goes into this one transformer. It depends on the resistances of the transformers, on the line lengths, and on a lot of things. So it's not trivial. But for that storm, we did have also Hall probe data from nearby substations, and we did have electric field data, and that just goes to show that what we can pick up with the differential magnetometer method is actually directly related to the electric field and to the GICs measured in the probe. There's only the difficulty I was trying to say, that line currents, line GICs are not exactly the same as the ground GICs. And just to like make a little bit of a better modeling effort there, we also went and collected some MT data around there to get a better estimate for the electric field that goes into our modeling, because I felt the thin sheet model with the 10 by 10 kilometers wasn't giving quite the right answer. So we just went to the same place and collected MT data, which will allow us to predict electric fields that we can then put into correlation with the GICs that we observe with the DMM method. And that's just a plot I usually have to show to non-MT audiences, because they don't believe that the simple equation of E equals Z times B actually holds. And then I always have to show that, saying, yes, we can't really reproduce that the electric field here in black is observed, and in red is the predicted using the impedance sensor, that it's not exactly the same, because you do have drift and things which are of course not explained by the impedance sensor, but which will still be in the data. But it's basically just a filtering thing that you probably have to do to the real data to make it look exactly the same. Yes, and then we did some subgrid modeling. So saying, okay, we look at the site where we do have the DMM system installed, and we just model the line GSE and ground GSE flow during this one event, during the August 2018 event. And for that, we did have to do a really detailed analysis of the subgrid, because it actually turned out that the two parallel lines we were running it under weren't actually grounded in the same places. So you do get these imbalances, and also there are different grounding resistances, earthing resistances, sorry, at the substations, and these will influence where the GSE runs into the ground in that way. So that took a little bit of thinking, and then we could actually show that our model is roughly showing what we are collecting in our data, using the electric fields that we predicted with impedances. So that was the component there that was quite important. Since then, I mean, the instruments have been around and collecting data for the last 3 years. Two are still in the ground. I haven't been able to visit them, but it's quite a nice data set, and that's also something we're making available, which is specifically interesting for the UK, because it's a GSE proxy, but it's actually also electric field proxy, I think. And there's quite a lot of interesting effects you can see in that data set. Time delay between the GSEs when you look from north to south, which is something that the network providers are interested in. So something we have to investigate, see where that comes from. That's kind of how we visualize things. So you have the magnetic indices, and then you can see, okay, which of our sites was running at that time, and then you can make an analysis based on the data. Couple of sites, these are provided from my colleague Gemma Richardson. She's been doing work on the British Pipeline Network, which, as I said, is also technology that is influenced by space weather and that can take damage and hits from space weather. So it's something that people are interested in. She kind of made a first attempt to quantify it with a model. We do not have any direct GIC observations from pipelines in the UK. I think there's one in Finland where they actually do have a probe on a pipeline. So that would be something good that we also should need, like some directly observed data to validate our model. But just to say that there's a lot of gas transmission pipelines in Great Britain. It's like thousands and thousands of kilometers, and the typical life expectancy is 40 years, and everything is quite old already, and it has this cathodic protection. So there's some galvanic current flowing in there to protect it against erosion, and that's set to this 0.85 millivolts. So, and if you have negative currents flowing in it due to the electric field induced by space weather, that of course goes against the corrosion and reduces corrosion. So, and that damage is not thought to be just instantaneously, it's also a cumulative effect. So if you have a lot of events happening, a lot of induced electric currents, that will degrade the corrosion protection in gas pipelines. And she went again and looked for what's available actually from the, about the topology of the grid. And it's the same thing. There's a lot of things in the open domain, but not everything. And a lot of things she had to assume or find somewhere from other information. Yes, and this is how you could visualize the pipe to soil potential in gas pipelines in the UK, and it's for 2 different events. I know they look quite similar, but they are not, like the March 1898 storm. It's quite a bit bigger, and has like if you look at the total PSP in the network, it's of course much higher. But the biggest PSPs obviously occur where the lines are the longest between connection points, but also obviously with the latitude. But it's something to quantify at least now, which is quite useful, and it's one of the outputs that we are, the BGS, the Geomagnetism Group, is providing to stakeholders. And that's just to say where we are at the moment. So we are really more concentrated on services and operational outputs. So stakeholders in the UK, that's the Met Office, want quantification of real time and a possible forecasting. So we have a project where we're trying to also make a forecast of GICs and pipe to soil potentials by using forecasts of the ground magnetic field derived from these solar, wind, and magnetosphere coupling models. And then we're going to put it through different versions of calculating the electric field I know right now we're using the thin sheet model, but we do have the plan to replace it with anti-impedance derived fields and do some tests also with full 3D models once we have them. Yes, and that's just basically where we are right now. This is some conclusions. And I know it's been 45 minutes of really a lot of material, and I haven't touched on a lot of different things. So I haven't touched on like extreme value evaluation of electric fields and of geohazards in general. So there's a lot of study about that using historical records and different methods to quantify how big it actually can be. So I left that out a little bit, but just to say that I hope I gave you an idea that extreme space weather events are hazardous to modern infrastructure, like power lines, gas pipelines, touched on railway communications, and that comes through the coupling of the solar wind with the Earth's magnetic field, giving rise to these induced currents in the ground. And space weather research in itself has now collaborators from very many different communities, and EM is just actually a new player in something that has been going on maybe for 20, 25 years. So there's a lot of new possibilities for collaborations and new projects, but it's also challenging because there's different terminology again for things in different communities, and communication is always an issue, and we have to kind of, we're often asked to validate our models and how to give justification, why our methods actually work and how they work, and that has to be taken into account when like considering everything. And just to say that to model the impacts on ground infrastructure, you need quite detailed knowledge of the magnetic field, the electric field, and the actual infrastructure topology that you want to look at. And as always, it's good to have more and good MT data, because that helps us to give realistic ground electric fields, which are quite vital for the quantification of hazards on technology. That's my last slide, just some images, and thanks goes specifically to my colleagues and to collaborators. And I can take some questions. Thank you.
Well, thank you very much. I'm clapping on behalf of all the listeners. Absolutely wonderful, Juliana. Just the breadth of work that can be done in space weather. I'll use my prerogative as the moderator to ask the first question, and that is, we know that the sun has a 11-year solar cycle, but and I should know the answer to this, is the energy within a geomagnetic storm, does that also cycle? Are the storms larger during high sunspot number years?
I think that's not quite the connection, but there's more occurrences of storms and of like solar flares in the active phase of the sun. So it's not that during the quiet phase of the sun you don't have any and cannot be a big CME or so, but I think it's more about the frequency of events that definitely relates to the position of the solar cycle.
Yeah, I thought so. So we have a couple of questions, and can other people please throw your questions in? I'll read these out aloud so they get into the recorded version. So the first one is from Joanna Ribeiro, who asks, why did the UK opt to use the thin sheet method?
Yes, so the thin sheet method is a good approximation if your underlying model is good. And I think what it shows is that the actual data is a bit missing in the UK. So there are a couple of MT surveys, and I think they based the underlying 1D connectivity blocks that I was showing. Those were based on MT surveys, but there's no countrywide MT survey. So you have to base it on something. And the thin sheet, I think, was a good idea because it has these computational advantages that it's really quick. And if your underlying model is a good approximation, it also gives a good answer. It's just that you need to have a good underlying model.
We have an interesting question from Leo Fox, and that is that the estimated economic impact of a Carrington event was approximately £15 billion without mitigation. What mitigation measures are feasible?
So the network providers aren't like too open about this, what kind of strategies they have in place, but there are some hints because like through our DMM study, for example, of the GIC modeling, we're trying to find the places in the grid that would be most vulnerable to GICs because of the underlying geology. And if you can tell them these places would be specifically vulnerable, there are ways to mitigate it by either like shutting down like a segment of the line, or by having there's also generations of transformers. So older transformers are more prone to damage, and newer ones they have like an X. I just saw a picture of it. It's just like a box, I guess, and it means that it's not completely grounded in there, so that the GIC can't actually flow into the ground and into the transformer there. So there are ways, but the thing is about transformers, I think the problem is that once you have a damage, these things are not only expensive, they also takes a while for them to be produced, and they're really huge, and they are not being produced everywhere. So it's more if you had a really big blowout in different places and you had to order replacements, and you don't have any in stock, that would be the problem. So I think it's a combination of making the transformers that they have more resilient to damage from GICs, and to have some more spares, and to have a strategy to maybe like mitigate the risk in the grid when they have warning, because there are some warning period. I didn't show this, but at Carrington, like a solar flare, there is some warning time that we would have, and where we could. In that TV show, they had the warning time of 2 days, and they knew in 2 days everything's going to shut down. So that's kind of anticipated that there would be some warning time.
Yeah, Peter Walker asks whether it's possible to compute a transfer function directly between the current induced in a line and the magnetic field measured near the line.
Yeah, I didn't talk about this, but there is actually also an approach where you calculate transfer functions in a way between the GICs and the magnetic fields you observe somewhere else, because what you probably wouldn't have a magnetometer next to your line. That's just for our experiment now, but you would maybe have it for a little while, and then you would have the geomagnetic observations that you always have, like from the observatories. So I'm aware of at least one thesis where somebody tried this, yes.
And Ramesh Singh asks whether natural hazards occurring on Earth can influence magnetic fields observed by GOES, the satellite.
Well, I think the solar wind just goes in one direction. I don't think, I'm not a solar physicist. I don't know if there would be upstream effects if you had something on it. I mean, there would be rather small, I think. So it's probably not a first order influence.
I remember years ago when I was doing some ground-based measurements, and my colleagues were doing ionospheric work in Scandinavia as part of the International Magnetospheric Study, that we found the current systems in northern Scandinavia, actually in the aurora, seem to follow the coastline. So there is some feedback between ionospheric current systems and Earth structure.
Okay. Yeah. Yes, with Earth structure, yes, definitely. Yeah.
So Juliane Chen asks, well, first says, thanks for the presentation. Can I ask, does the way using empty impedance to estimate GICs work at high and mid latitude regions, as the plane wave assumption might not work?
So at high latitudes, I can't really speak for that, but I mean, making MT estimates in high latitudes is already challenging, I guess, depending on your frequency range, because you do have the electrojet. So, and your plane wave can be, your plane wave assumption can be violated. I can only say for mid latitudes, the comparisons I made is, I think it's a fair estimate. So it's something you have, and if you realize that it doesn't 100% explain your field, but it gives a very good estimate. So
yeah,
it goes into uncertainty in a way, like unless you model the source, which some people are doing, obviously. So some people are modeling the full current system. And then if you do also have a 3D model of the conductivity, you can model the non-plane wave part of the field, obviously. But it's all a question of what is feasible and how accurate do you want to be.
Yeah, I remember from when I was doing that sort of modeling again in Scandinavia, that beneath the current system, your apparent resistivity is underestimated. So that means the E field is less than you would expect. But at more than a skin depth away or half a wavelength away. It's more than you would get from a plane wave. So Michael Torta asks, with your differential magnetometer measurements, are the magnetic field measurements noisier at the magnetometer under the power line than those at remote place? We have realized that with our similar experiences, especially during the day, less during the night hours.
Interesting. I haven't seen that. Like, I mean, we chose places which are relatively quiet, and I was really surprised, but it's, those sites are not that noisy. The magnetic field measurements under the power line are not very noisy. There is sometimes, I mean, you can clearly see the GIC signal, and there's a little bit high frequency noise. But in general, they're not bad. So, and I haven't observed this night and day thing, so I would have to probably look for it a bit better. I think I usually look at storms, you know, like 3 days of a storm, and you see the activity and you see the difference between the systems, but I haven't looked at it in night and day.
Okay. Just one more popped up. Raha Hafizi asks, how can forecasting GICs help to minimize the hazards?
Mm-hmm. So that's about the mitigation strategy I was talking. So if network providers have a bit of warning, they are able to do something about the threat to their infrastructure. It's the same with, I mean, don't know much about satellites or like GPS operators and stuff, but if they do have a bit of warning, they can either like use other systems, or they can just give a warning out. So in a way, forecasting the GICs, what we're trying to do is like saying, okay, due to the data from the solar wind, we predict that the magnetic field variations on the ground are going to be like this, and then putting this into our electric field and infrastructure model will say this is kind of the magnitude of effect we can expect. So yes, forecasting helps mitigating hazards is the answer, I think.
Okay, I think you seem to have answered everybody's questions, Juliana. So if there's no more questions, I'd like to, on behalf of all the listeners, thank you again for an absolutely wonderful presentation. And I'll just get the screen back from you to remind everybody about next week's EMinar from Colin Farquharson on EM-MT inversion. Will be at midday UT time, whatever that time is for you. And thank you, Juliane, again, and thank you everybody for listening. And we'll talk to you all next week. Bye for now.